I'd like to talk to you about visualizing spatial data, and this is an area that I have a ton of interest in, and I'm going to have you watch another related talk that I'm going to reference several times throughout this presentation, How Spatial Polygons Shape Our World. And I just want to start with the idea that the problem with maps is that the world looks like a map. So if you are up in an airplane and you're looking down out the window, what you see out the window looks vaguely like a map. And we don't have that same problem with other types of data visualizations. So if you have a scatter plot, it might seem true because it's been made with statistical software, but it doesn't look like the thing that it's actually representing. Versus maps kind of look like the thing that they're actually representing, which makes them feel more true, even though they're not. So in that talk, How Spatial Polygons Shape Our World, I lay out that there's sort of three main types of geographic data. There's points, lines, and polygons. And in that talk, I'm mostly focusing on like when you draw maps. So when you have points, it might be the locations of trees or the locations of houses or something where you just have a specific latitude and longitude position. Lines, I say maybe that's roads or rivers, something like that. And polygons are any area that's defined around a particular part of the map. But I want to think about this more specifically in terms of data visualization. So when I think about using points as a mapping for data visualization in spatial visualization, one of the examples that I think of is the Census Dot Map. And so this is still using the 2010 census data. I'm hoping they will update it with the 2020 census data once that's released. But what the authors of the map did is they disaggregated all of the census data and they made a map that has one dot for every person in the United States. We know there's problems with the census. There are people who get undercounted, such as people who are homeless or people who are undocumented. They often are more hesitant to respond to the census or it's hard to reach them. But the census tries to account for those problems. So the idea of this map is that there's a dot for every single person. And the one that I've shown you here, I have the map labels over the top, but you can also turn those off and just see the shape of the population based on just those dots. So I think this is a really nice use of dots that are mapping the locations of people, and then the colors are representing the race of the person. Here's another map that uses dots as a mapping. These are showing the share of foreign investment that is Chinese. And I think this is kind of an old one. This is from 2005 to 2013, but we're using dots as a visualization method. And we've talked about this project by Nathan Yao before, where the dots represent Walmart locations and the colors are whether it's Walmart or Sam's Club. The size of the dots is just showing you the ones that are appearing at the moment, and then they're all the same size. So that's letting you see the points over time as well. When we think about lines, it's a little bit harder to think how you could map something in the data to lines on a data visualization. But you can imagine lines being used to connect between locations. So there are lots of like flight maps that have this kind of visualization. I also love this piece by Ben Fry. It's called All Streets. And the only thing that is being drawn on the digital paper here are the locations of streets in the United States. And what you can see is the population centers, the population density, and you can also see geographic features like where rivers are, or I think that's kind of the Appalachian Mountain Range there. So there's fewer streets because of the elevation changes. So you can really see something about the land just based on those streets. And I think I have another shot from this. Here we are looking up at the border with Canada. and you can tell that things are getting less urban, more forested, because there's fewer streets that are visible there. So you can really see the density of streets in these urban areas, and then the less dense areas where it is rural. And then polygons, that's the focus of the talk that I'm going to have you watch about spatial polygons. But just to give you a start, the most common way that you'll see polygons used in data visualization is in a choropleth map. So choropleth maps take a polygon, and so a really common one would be the states in the United States, and then they color the polygon according to the value of some variable. So this is a map which shows the most commonly spoken language other than English for every state in the United States. And as you can see, in most states, that language is Spanish. And then I think they go one more layer and they say, what if we didn't consider English or Spanish? What's the third most commonly spoken language in that state? And again, they've colored the polygon according to the value of that variable. So you can see all the states where the third most common language was German, or Hmong, or Vietnamese, or Navajo, whatever it is. And so we see choropleth maps in a ton of situations. I'm not going to give a ton more examples in this section, but we'll see them come back in a little bit. And then one piece that I don't talk about in that talk, but is also commonly visualized, is a heat map. So a heat map is a visualization where you don't have just points, and you don't have simply filled in polygons. You have colors that move from one to another over a gradient. So this is from the book Speaking American by Josh Katz. He surveyed a ton of people and created these visualizations of dialects in the United States. So there are people who call this receptacle a garbage can, and those who call it a trash can, and you can see some regional variations. It's not just the north and the south. There are pockets all around that have different regionalisms. Similarly, we've got soda, pop, and Coke, and you can see kind of a heat map of sort of fading from soda to pop, from pop to soda, and then to Coke down in the south. So this would be a heat map. This is a cartoon from XKCD that is laying out some of the problems with heat maps. One thing that you want to be really careful with is making sure that your heat map is not just a population map. So if you have a map of the site's users and also a map of subscribers to Martha Stewart Living, they are going to be concentrated in high population areas. So you don't want to sort of say, there's some correlation is causation, and think that you have this great pattern, because there's just going to be a lot of people in a particular group in a particular area that has high population density. And then this leads me to another thought about maps, and this is from a paper by Andrew Gelman and Philip Price, and it's called All Maps of Parameter Estimates Are Misleading. And I talk about that in the other talk, but I wanted to give another more perhaps relevant example related to COVID. So here is what they mean when they say that all maps of parameter estimates are misleading. If you show raw numbers in a choropleth map, that is going to highlight high population areas. So this is a map of confirmed coronavirus cases in the state of Ohio. This is a pretty old map. I don't remember when it's from, but it's basically just highlighting the high population areas. Because if there's more people there, then there's going to be more cases there. So you might be thinking, okay, I'll just be clever and I will divide by the number of people that live in the area, the county or the zip code or whatever it is that you're plotting. But the problem with that is if you show the rate, so this is the amount of cases per, I think, 100,000 population, it's going to show high variability in low population areas. So if you have a county that has very few people living in it and no one gets coronavirus, it's going to look like there is a rate of 0%. And if you have a very low population county and it has one case of coronavirus, it's going to look like it has a huge, huge high rate. And then the areas that have large population, so things like LA or San Francisco, because they're so big, they're going to have about the average rate. So you're going to see high variability in the low population areas and low variability in the high population areas. So the question is, Gelman and Price say there's no solution. Is that really true? Well, maybe, but I know of a couple solutions. So one that I like is by Michael Correll and Jeffrey Heer, which is called Surprise, Bayesian Weighting for Debiasing Thematic Maps. So they make these surprise maps by saying, okay, we know that if we do absolute numbers, there's going to be more of that in the high population areas. So that's image A. And these maps are showing the event density of mischief. It's a category of property crime in Canada, like egging someone's house or TPing their trees. So there's high rates of mischief in the high population areas. But then if you do it per capita, you're going to have the high variability in those low population areas. That's figure B. And then figure C would say, okay, I'm going to take both of those as prior beliefs, that we're going to have high rates in high population areas and high variability in low population areas. And I'm going to use Bayesian methods to say, where are things different than we would expect? Are they higher or lower? And so you can see where there's, higher or lower rates than we would expect. That's a little bit complicated for the average layperson to understand. So I liked this strategy that the New York Times was using in 2020, where they said, we're just not going to show the areas that have very low population density. So instead of having the whole Midwest look like a solid wall of red, like we saw a few slides ago, we're going to just eliminate those places in the Dakotas and Wyoming that have really low population density, and we know they're going to have that high variability. And then we'll just show you what's going on in the areas that have a population over a certain threshold. And there were criticisms of this approach as well, so I don't think this is perfect, but it is an interesting strategy, and I think it's one that a more general audience can understand. So here it is a little bit larger in case you wanted to see it. So you can see population centers like in Minnesota and Wisconsin, and then moving out to the east, we have higher population density over there. On the west side of the country, we have a lot of low population density areas. And then just one other thing that's come up with choropleth maps, and specifically with COVID, because we've been looking at a lot of them over the past year plus, is that if things are changing over time, you should watch the legend. So there was a lot of criticism of the COVID maps that were coming out of Georgia because the legends were being automatically generated by whatever analysis software they were doing. So on 1 week, they used the software. They said make a map and use 6 breaks, and so the software split it into none, 1 case to 620 cases, 621 to 1,070 cases, and then the highest bin was 2,961 to 4,661 cases. But then the next week, they input the data and they said, make this into 6 breaks and do the colors accordingly. And that time, the highest bin that was read meant 3,769 to 5,165. So if you were looking over time, you would think that things weren't actually getting worse. And so the strategy to combat this would be to set the breaks in advance and keep them consistent over time. The New York Times was trying to do that, and actually there turned out to be so much COVID that they had to change their scales a couple several times because they set them and then the whole country went completely red. And so then they had to bump up the scales again. So again, it's a really challenging thing when you're doing visualization kind of an unfolding situation in real time.